Hi everyone! In this video, we'll try a more complicated example of an improper integral. I'll encourage you to pause and get as far as you can with this example on your own, and when you're ready to look at the solution, let's continue. First of all, we need to identify all the improper features. First of all, notice that one of the endpoints is infinite, but also there are some discontinuities at x equals 3 and x equals minus 3, because those values give us a denominator of 0. Now, in order to go from 1 to infinity, we'd need to jump over one of these discontinuities. So instead of going from 1 to infinity, we instead go from 1 to 3, and then go from 3 to infinity and add these results together. This is a good start, but you should notice this second term is now improper at both the endpoints. The lower limit is a discontinuity, and the upper limit is infinite. And since there are two improper features, we should split this integral up even further. Okay, so we've still got this integral from 1 to 3 as our first term, but then my integral from 3 to infinity should be split up further. We could instead consider the integral from 3 to 4, and then add the integral from 4 to infinity. I chose 4 because that felt natural to me, but there's certainly no reason it has to be 4. In fact, any value which is larger than 3 would do the job just fine here in place of the 4. So whatever your preference is perfectly fine. Our original integral has now been split into these three terms, and each of these only has a single improper feature which appears at an endpoint. If that were not the case, we would just continue splitting these things up, but for now, we're ready to start calculating these. In order to calculate them, we know we'll need an antiderivative of this function, so let's just get that part out of the way now. There's more than one way you can proceed here, but I think the easiest way is to notice the difference of squares in our denominator. If we factor out the negative, this resembles the formula for inverse hyperbolic tan. To see that even more clearly, you can consider expressing 9 as 3 squared, and then comparing this with your formula sheet, you can see that a equals 3 in the formula for inverse hyperbolic tan, which gives us minus 1 over 3 inverse tanh of x over 3 as the antiderivative. Another way to do this would have been forming a partial fractions decomposition, but I think that would have taken significantly more effort, so this is my preference. Okay, so let's start by calculating this integral, which we labeled as 1 on the previous slide. We hope this integral diverges, because if it does, then we don't even need to bother with the integrals labeled as 2 and 3. But let's see. First of all, we just found this as our antiderivative. And now, since x equals 3 is a discontinuity, we can't evaluate from 1 to 3. We can evaluate it from 1 to t, and then let t approach 3, but from the left side in this case. It's from the left because we're going from 1 up to 3. Now let's plug in our endpoints. Both of them have a common factor of minus 1/3, so let's just pull that out front for simplicity. When we plug in the upper endpoint, which is t, we get tanh inverse of t over 3, and then we plug in the lower endpoint, which is 1. Then we apply our limit to this result. So we let t approach 3 from the left and see what happens. In our first term, we notice 3 over 3 can be simplified to a value of 1. And this is where I would expect a lot of students to get stuck. How do you calculate the value of inverse hyperbolic tan? If you check your formula sheet or go way back to the part 3 video on hyperbolic functions, you'll find I gave you this formula which can be used to perform these calculations. If you don't remember this formula, just trust me for now and you can go back and review that video later. Let's go ahead and apply this formula and calculate the value of our first term. And then similarly, we'll do the same thing for our second term. For the first term, the fraction inside the logarithm simplifies to 2 divided by a small positive number. And you can check that for the second term, the fraction simplifies to a value of 2. Pause and check this as necessary. We know that when a positive number is approaching 0, we get an increasingly larger result when we divide by that number. So we can see that this fraction is approaching positive infinity. And when we take the log of an increasingly large value, the result is still an increasingly large value. So we can see as a whole, this first term is approaching infinity, and you can check the familiar graph of ln x to convince yourself of that if you need to. Now, subtracting 1/2 of ln 2 is not going to stop this result from going to infinity, but it'll end up being negative infinity due to the negative in front of these square brackets. If you go back to the integral we were asked to calculate, as a first step, we broke this up into these terms, which we labeled as 1, 2, and 3. We just found that this first term represents a divergent integral. And because of that, we don't even need to bother calculating the other two terms. Instead, we just conclude that the original integral is also divergent, and that concludes this example. Aside from being a reminder of certain things from your formula sheet that you might not have thought about for a long time, the main takeaway from this example is that sometimes you need to split the improper integral into more than two terms. In general, split it as many times as you need to so that each term has one improper feature at an endpoint, and after that, you should be good to go. That's all I have for improper integrals, so I'll see you next time.